Hello.
Hello. Hey.
Oh, Aya is here too. Hello, Aya.
Hey. How are you doing, guys?
We're good. How are you?
Fine. A little bit tired. It's so hot in here.
Do you want to start?
Sure. Who's presenting today?
I'm presenting the second part of part 22.
Oh, nice.
Okay. Oh no, I have to go on the lights. Okay, so today we'll go over some properties of the quotient map and the quotient space. So for one thing, if we have if we have a quotient map and if we have A, which is the subspace of, so let's have, this is our quotient map, P mapping X to Y. If A is a subspace of X, the map which we get, Q, is not necessarily quotient map as well. So we're going to prove this in our theorem 21. We will prove that Q will be a quotient map if A is either open or closed in X, or if P is either an open or closed map. So here is the first part of our proof. And we have to start with these two equations. So the inverse, Q inverse of V would equal P inverse of V, where V is a subset of P of A. Since it's a subset of P of A and A is saturated, so when we restrict P to Q, we would still have the same result. And the second equation which we have to prove is that if U is a subset of X, then P of U intersecting A equals the intersection of P of U and P of A. So we know that P of the intersection of U and A is a subset of the intersection of P of U and P of A. And to prove the reverse, we will have Y equals P of U equals P of A, where U is in big U and small a is in big A. And since A is saturated, it would contain P inverse of P of A, and thus it would contain U. So U would belong to the intersection of A and U. And then basically we get that these two are equivalent. So if we have U belonging to the intersection of P of U and P of A, it would also belong to U intersecting A. And once we have that, we can go to our second part. So basically I have the entire proof on the screen. I'm just going to read it. For the rest of the proofs, I have left some parts so we can do them together as an exercise. So if we have a subset V of P of A, for which Q inverse of V is open in A. Let me just put P and Q in the board. So P maps X into Y, and it's a quotient map. And Q is mapping A into Y, where Q is restricted B and A is a subspace of X. I don't know. So A is a subspace of X, and these are our two maps. So we have V of P of A, for which Q inverse of V is open in A. So first we'll consider the option where A is open in X. So Q inverse of V would be open in A, and A is open in X. Then Q inverse of V is also open in X, and Q inverse of V equals P inverse of V, and what we proved up here. P inverse of V is open in X, then V would be open in Y because P is a quotient map. So V would be open in P of A, which equals Q of A, and Q would be a quotient map. And let us consider the other option where P is open. So we have Q inverse of V equals P inverse of V, and Q inverse of V is open in A. So P inverse of V would equal U intersecting A for some set U, which is open in X. And P of P inverse of V equals V since P is surjective. So we have this equation here. V would equal P of P inverse of V, which would equal P of the intersection of U and A, which would equal this thing, the intersection of P of U and P and A. So P of U is open in Y since P is an open map. And then if we recall our definition of the subspace topology, it is that basically our elements of our open sets in our subspace are intersections of our subspace with an open set in X in this case. So V would be open in P of A. And now we get that, again, Q is a quotient map. And since our theorem states that we can also prove it if A is open or closed, or P is open or closed, basically everywhere where we have open, if we switch it to closed, our proof would work again, since we have used properties of open sets and functions, which are analogical to those for closed sets and functions. So a few more properties of the quotient space are that the composite of two quotient maps is a quotient map. Since we can say that a P inverse of Q inverse of U is equal to the composite of P and Q inverse of U, or just an easy way which I taught for myself. So if we have P which maps X to Y, and then we have Q which maps Y to Z. Oops. So basically, for every open set V in X, P of V would be open. Since it is open, Q of P of V would also be open or respectively closed. And surjectivity would also be kept. This is just a simple way which I put it in my mind. It's not from the book. And the Cartesian product of two quotient maps is not necessarily a quotient map. We have an example. Space. So my internet is getting bad, so I don't know if you can hear me well. Okay, next is our theorem 22.2. So this theorem and its corollary are used to determine if a map out of a quotient space is continuous. So if P mapping X to I is a quotient map, let Z be a space and G mapping X to Z be a map that is constant in each set P inverse of Y for Y belonging to big Y, then G induces a map F which maps Y to Z such that the composite F after P equals G. And the induced map F is continuous if and only if G is continuous, and F is a quotient map if and only if G is a quotient map. So here is part of our proof. So for both claims, I have proven only one side, and we will do the other side as an exercise. And okay, so just a diagram which makes it easier to think about the problem. So here is our function G, and here are our functions P and F. So here is our G mapping X to Z. Here is our P mapping X to Y. And here is our F mapping Y to Z. Okay, so we know that for each Y belonging to big Y, G of P inverse of Y is the 1-point set in Z. And if F of Y denotes this point, then for each X in big X, F of P of X equals G of X. And F is continuous, then G equals F after P is also continuous since P is a quotient map, which is already continuous. So, okay, so now maybe does someone want to prove the other way to try to prove that if G is continuous, it follows that F is continuous? I don't like picking names. Does anyone want to try?
Well, wait, isn't the proof just written here? Or am I not getting something?
It's the proof that if F is continuous, then G is continuous. And now we have to prove it that way. If G is continuous, then F is also continuous.
Oh, okay, okay,
Did
okay.
I put it wrong? Wait, if X continuous, then G is also. Yeah, so we have to prove the other way around now. If G is continuous, then F is also continuous.
Okay, give me a second. Sorry, can we so can you remind us like initial statements? So which of them is a quotient map, or are all of them quotient maps and stuff?
P is a quotient map, and G is it's constant on each set, P inverse of Y.
Sorry, and G is what?
It is constant on each set, P inverse of Y. It's basically this thing. G of P inverse of Y is a 1-point set in Z.
Okay, okay, okay. Gotcha. Because basically we know that G is continuous, meaning that if we take an open set in Z, then means that G inverse of that open set should be open in X. And because P is a quotient map, we have a strong, how do you call it? A strong continuous property. So that means that that means that basically P of G inverse U, if U is at open set, should be open to. And so that's kind of getting into the, yeah, I feel like that's basically the proof. Give me a second. I just have to show why G inverse is exactly F, which is, well,
I think there's an easier way. Instead of going with saying that P of G inverse is open, you can go with J inverse equals P inverse of F inverse, and P inverse would be open, and then
can you say that again?
I'll try that. Okay, so you can go right here. So you can go with G inverse of U equals F. Okay. Inverse of P inverse.
Oh wait, yeah, that's exactly like the statement I need. Do we already know it? Like, did we ever prove it? Or I mean, you can, yeah, I can see you can easily prove that if you, yeah, that should be fine. Yeah, second. Wait, sorry, I don't get why you wrote
Oh, it should be that.
oh
Sorry?
I don't get why you write P inverse of U, because that's, yeah.
I think that should be better.
Yeah, I mean, and then I think my proof goes well, because basically if we have this statement that you just said, we can say, you mind if I write on the board?
Sure.
A second. Okay, so basically if we do something like, let's say G minus U should be open, and then basically because P is a quotient map, then P G minus U should be open too. And then yeah, and then basically what it means is that we always have and this just should be F minus, I say, yeah, that should be it from F minus U. This is
I can't hear you.
I think that, can you hear me now, or is it still bad?
Yeah, now I can hear you.
Okay, sorry, my internet is still really, really bad. I mean, I think basically what happens is we just say because G is continuous, we know that G inverse U is open. Then because P is a quotient map, we know that G inverse U is open. And then from your statement, we easily get that F inverse U is just equals to P G inverse U. So that means that P inverse U is also open. And then we just basically got a logical link. U is open, then F inverse U is open, which means that F is continuous. Is that?
Yep.
Yeah.
That's right. Thank you. Okay, so our second statement in the theorem. Okay, I'll just first remove these marks. Yep. So our second statement in the theorem is that G is a quotient map if and only if F is a quotient map. So I have put here the direction when we know that G is a quotient map, and we have to prove that F is a quotient map as well. So if G is a quotient map, since G and P are surjective, F would also be surjective. And if F inverse of V is an open set of Y, P inverse of F inverse of V would be open in X because P is continuous. And since this set is the same as G inverse of V, G inverse of V is also open in X. And since G is in quotient map, V would be open in Z. And we know that F inverse of V is open set on Y, and we prove that this V would be open in Z, and also we know that F is surjective, so F is a quotient map. And then the other direction is quite simple. Its solution is in one of the previous slides. So I will ask Zikong to give us the other direction, where we know that F is a quotient map, and we have to prove that G is a quotient map. someday I will get an iPad with a pen and I will write pretty stuff on the board.
So G can be seen as the composite of F and P, and F is quotient map and P is a quotient map. So the composition of these two is also quotient map. So G is a quotient map.
Yeah, that's right. So we proved our theorem, and we can move on to our corollary from this theorem.
A very quick comment about the theorems. You can see that Tadara, you just draw a graph here, right? The F, G, and P, right? The graph here. And then you can see that, okay, G is actually the composition of P and F. So this kind of graph, sometimes we also write it in this way, which means if you go in this direction or in the other direction, these two will be the same, okay? And then based on this kind of graph, you can say a lot of very good properties, like in the theorems, well, about P, if something happens in P, then something must happen of F and G, and so on, okay? This kind of properties. And this kind of graph, it has a name, it's so-called a commutative graph, and which means F can be replaced by P composed with G. And later you may see some other kind of commutative graph, something like this. You go this way and you go this way, they are the same. And maybe you can also go this way, and so on. Well, this kind of thing is, well, although I didn't learn that because this is something very deep in the future, it's very important if in the future you are interested in algebra, okay? This kind of graph, it means a lot of things. And it's in some cases, it's quite essential, okay? Yeah, this is just a quick comments.
Thank you. Okay, so I will move on to our corollary. So we say let G mapping X to Z be a surjective continuous map, and let X star be the following collection of subsets of X, where X star is G inverse of Z for every Z in big Z, and X star has the quotient topology. So we want to prove first that G induces a bijective continuous map F mapping X asterisk to Z, which is a homomorphism if and only if G is a quotient map. And then we want to prove that if Z is Hausdorff, X star is also Hausdorff. So just before we go into the proof, so if you remember from our previous theorem, we have this graph, and we knew that P is a quotient map, and we knew that basically G is constant on each set P inverse of Y for Y in big Y. So here we have the same situation. It's just put in a little bit different words. So a graph that helped me to picture this looked like this. So if we have I will put the graph here. Okay. So if we have our X as, wait, this is our X, this is our Y, this is our Z, so this is our Z, okay. So our Z is 4 points, and our X is a circle. So each of, it's a circle, but yeah. So if we have 4 quarters of the circle, so this point would map to this quarter, this point would map to that quarter, and this point would map here, this point would map here. Actually, the other way around, like that. So this quarter maps in this point, and so on. And then we can imagine, okay, that's really, okay, just have me imagine it. So this is uncut pizza, and then we cut it into pieces. So we have 4 different sets. Again, so this set would map to this set. This section would map to this set, which would then map to the same dot here. And this section would map to itself here. It's just like the difference before you cut the pizza and after you cut it. And it would map again, so this part maps here, so this part would map here, and so on. I'll just finish it. And it looks pretty ugly. It was much prettier in my mind than it's here. I hope it helps you imagine it at least a little bit. If my drawing is too ugly, you can try to recreate it on your paper if you think it will help you imagine the situation. And yeah. So I think I can move on to the proof. So I will move my pretty grass. Sorry. Okay, so here's our proof. So as we saw, our previous theorem is perfectly applicable here for G, P, and F. This time, the only difference is that X is mapped into X star, not into Y. Okay, so here's a part with which I will need your help. So by the previous theorem, we know that G would induce a continuous map F. So we know that G is continuous here. And here the book says that this helps us know that F is bijective. Now, I probably missed something, but I was not able to explain to myself why it follows from the fact that F and G are continuous, that F is bijective. So maybe someone can help me? Hey guys, anyone? So we know that P is a quotient map and G and F are continuous. P and G are surjective. And we need to get that F is bijective.
Hey, for Zukan and I think this is well, this kind of problem to see why this F is bijective is kind of similar to what we've learned about the fundamental theorems of homomorphism. I don't know whether you still remember that or not, but you can try to think about it and see whether you are able to prove it or not. It's kind of straightforward. You can try.
So if we know that F is a homeomorphism, we would know that it's a bijection and that F and F inverse are continuous. But I can't recall another connection between a bijection and homeomorphism. And in this case, we pretty much proved that it's a bijective function before going to homomorphisms.
So first, we know that F is a surjective, right? From P and G are surjective. So F is of course surjective, and we want to show that F is injective. So from the, I think from the collection, the definition of this X star is the collection of subsets of X. So if we are given two different Z's, like Z1, Z2, and they of course corresponding to maybe different X star.
Sorry, can you repeat your idea again? Okay, so maybe do you want to move on and come back to this after we finish? Because after this proof, I have 2 examples and my presentation is over. Sorry, do you hear me? Oh, someone is texting in the chat. Also, Zikangi saying, okay. So since we, were you here when we were discussing how we're trying to prove from this statement to go to that statement? So we know that P is a quotient map and G is yeah, so basically we're trying to prove it. We have not come up with something successful so far. How do we get the bijective part? I know that we get the continuous part, but I don't understand how we get the bijective part. Like in this statement? Yeah, sure. Do you want to go to the statement of the theorem itself?
No, I think it should be, give me a second. So we know G is surjective continuous map. And we know that it takes basically all the possible pre-images of all the points in Z. And because Z is surjective, then we just doesn't mean that we get every okay. So we get like some kind of open, we get some kind of a collection of open subsets of X. And then we give it a quotient topology. I'm not sure what it means by induces though. Like, how does G induces a map specifically? Oh, sorry. I mean, maybe we can just try to build F because it's not specifically given in here. And I mean, so, okay. So how about, I guess what they want us to show is that if G is a quotient map, then I guess they won't. I also don't see a problem there because for every image you get a pre-image. We just have to show that no 2 points Z have the same pre-image, and that would guarantee your inductive property, right? So if you assume G is a quotient map, the quotient map, then why wouldn't the preimages be equivalent? Then maybe that's because give me a second. Wait. If two preimages give different, that just cannot happen. Yeah, that's bullshit. That means that, yeah, because we have, so because G is just a function. It means that for one specific pre-image, there's only one output, which means that we cannot have two Z's having the same preimages, which means that at least G is injective. That's fine. And then basically, because we don't have any similar preimages, honestly, I really don't see a problem. Like, isn't F just an inverse function of G, and we just have to show that? Like, we just have to show that it's actually a function, which I think we can do more or less easily, right?
I don't quite understand your last sentence.
Yeah, let's just go to another one and think about it later, because I think it's doable. It just has a lot of like little statements you have to prove in between, which is a little bit tedious.
Okay.
Can you maybe because we're gonna have a solving problem day or something, so maybe you can like specifically remember this corollary so we can try to solve it later when we have that problem solving day or something.
I also think that we will have some time left today, because after this proof, we have 2 examples, and I'm pretty much over with the chapter.
Oh, nice. Oh, we over like entire second chapter?
Actually, yeah.
That's great. And how about we make a problem solving time on Friday? But how about we publish the questions beforehand? So if somebody wants to spend more time doing them, they can do them before Friday. And then on Friday we just try doing stuff.
Sounds good. Maybe we can pick questions from the chapters, from the parts which were presented.
Yeah, sure. That would make sense. Okay, then let's plan it for Friday and make a set of questions later. So what were your other 2 examples?
Oh, we have more proof. This is actually in the book. They just stated it's bijective and don't go into explaining why. So if we do this, we just take that F is bijective, then if F is a homomorphism, both F and P are quotient maps, and their composite G is also a quotient map. And conversely, if G is a quotient map, again, by our previous theorem, F is also a quotient map, and since it's bijective, F is a homomorphism.
Wait, I'm really sorry. I just got is our Z finite or infinite? Do we know this? Because if it's finite, then F is actually bijective. Like,
We don't know anything about our Z.
I mean, but the thing is that, well, I mean, the thing is that for every image you get only one pre-image and stuff. So by that, X star and Z already have the same number of elements, or the same how do you call it, like they are either more countable or uncountable, whatever. So there should be a bijection by default, because they just have the same number of elements. I think that is enough. Like,
Well, it doesn't matter actually because you choose F as an induced map, right? So even if X star and Z has the same number, same cardinal, this F may not be a bijection, right?
but how do we induce a map? Like, what does it mean to have an induced map?
This is actually, well, how you induce a map is actually introduced on the previous theorems, right? The theorems 22.2.
Wait, then I realized I don't remember the word induced there. What was it?
I think it's used in the language of the previous theorem again, and we say that. I will go back there. We
So
say
can we
again.
use the condition in theorem 22.2 this G, the property that G is a map that is consistent on each set, P inverse of a single element belongs to 1. Like for this corollary, and
Sorry?
I mean to prove that like F is actually an injective map, can we use the property that G is a map that is consistent on each set, P inverse of a set of a single element Y?
I think that's pretty much what I tried to do.
I think if we are given this condition, maybe we can prove that it is injective or
Well, if you try to think it's like in a group, in a group theory, it's basically you maps X to X star, and X star is somehow like this group will modulus the kernel, something like that. And then so the induced map must be something injection. So which is why if you think it this way, then the bijective is kind of easy to see. But again, how you can see it in this kind of context, in this kind of only in the mapping way, this is a problem, right? This is actually a problem for you to think how to write it rigorously. But intuitively, it just says that, okay, from X to X star is what? Is you just trying to make this kind of all the inverse to maps in one single point, right? And this is actually of the same spirit as a quotient group. Well, when we learn the group theory, well, maybe Tadera and Holly, you don't know this, but you can just try to imagine. You try to push everything and try to pass everything into one point by doing this kind of operation. I mean, try to pass every pre-image of one single point as one point. I think intuitively it's just this graph, right? You try in this kind of, well, commutative graph, you have a map from X, this is X, to Z. And what you're trying to do here is you try to do some kind of decomposition, and which you try to map X to some X star, where X star contains, instead of 3 elements, it contains only 2 elements, 1, 2, as a single element, and 3. And then you try to map from X star, which is 1, 2 as one element, and 3 as a second element, to Z, AB. Then F can be seen as a bijection. But anyway, yeah, we can postpone it later if you still get confused, and maybe see the example first if you want.
Okay. Well, go on. Yeah. The rest of the proof, it's again pretty straightforward once we know that F is bijective. If we can prove it. I'll leave it here just for a few more seconds. And here is our first example, example 6. So let me see my notes. Okay, so if we have X as the subspace, here is a very pretty graph from our textbook. So if X is our subspace from R squared, which is the union of line segments mapping 0, the quotient group from 0 to 1, cross N, for N in being a positive natural number, and Z is the subspace of R squared consisting of all points of the form X cross X over N, for X belonging to in the interval from 0 to 1 and belonging to Z plus. Then basically we have X being the union of countably many disjoint line segments, and Z is the union of countably many line segments which start from the same point. So then we define a map G which maps X into Z. We map it so T of X cross N equals X cross X over N, and then G is surjective and continuous. And if we define the quotient space X star such that its elements are the sets G inverse of Z in the space which we get from X by identifying the subset 0 cross Z to a single point, then G would induce a bijective continuous map F which maps X star to Z, but G would not be a homeomorphism. So to prove that it is not a homeomorphism, we have to show that G is not a quotient map. So we can go to, we define collection of points xn, which equal 1 over n cross n, and our set.
I'm sorry, I think in our textbook it said that F is not a homomorphism, right? Because G itself is not a bijection, right? So of course it's not a homeomorphism.
Yeah, I'm sorry. I'm so sorry. I will correct. There's just probably a better way to do it than this. Sorry for that. Okay, so we have the set A, which equals the collection Xn, and by corollary 17.7, which says that a subset of a topological space is closed if it contains all of its limit points. We see that A is closed in X, since it would go. It's not exactly continuous. Okay, anyway, I'll not talk about this, but basically its limit is not a point which does not lie in it. It goes up to infinity. And it is also saturated with respect to G. And G of A is not closed in Z, since it contains Zn, which equals 1 over n cross 1 over n squared. And the sequence of points goes in this way back to the origin, but it never goes directly to the origin, so the origin is its limit point. So it's not closed. So here we have a set which is closed and saturated, but does not. What did I write here? Sorry. Yeah. It's basically not closed, and it's not a quotient map. So G is not a quotient map. And from this, it follows that F is not a homomorphism.
So intuitively, what does this theorem tell us? Well, it just says that, okay, if you have a lot of straight line, right? The intuition is, if you choose all these kind of lines and choose this, their intersection with x equals to 0, right? And then try to pass it like the figure 22.7, on the right hand side of this finger, then this kind of operation is not continuous, right? So you try to do some paste, you try to manipulate it, but then it seems that this kind of, if you have infinite many lines, if you only have finite many lines, then you can do this, right? You can pass all these lines at one point, move them and pass them on one point. But if you have infinite many lines, then this kind of operation is not possible, right? If you try to do that by in the sense of topology.
Okay. And then we have our last example. So, mistakes in the chat. I'm happy to. So this example, intuitively, it was maybe okay-ish, but I found it a little bit complicated to write and stuff. So I hope that what I say will be of any help to you to understand better what's going on. And if not, it's explained really good in the book. So maybe the book's explanation will be better than mine. So, okay. We have space X, which equals R, and then we have X star, which is the quotient space obtained from X by identifying the subset Z plus to be a point B. And then we have our quotient map, which maps X to X star. And Q is the subspace of R consisting of the rational numbers, and I is the identity map which maps Q to Q. So what we're going to do is that we're going to show that P cross I such that X cross Q is mapped to X star cross Q is not a quotient map, even though both of our initial maps are quotient maps. So let me explain the graph first. So we have the collection of points Cn, which Cn, I'll just put it here, Cn equals square root of 2 over n, and basically we have here all points n cross Cn, and we call Un the space which is bounded by X equals n minus 1/4, X equals n plus 1/4, and the lines which go through n cross Cn whose slope is -1 and 1. But neither, so the space which is bounded here and here forms Un. And n cross Cn does not belong to that space, neither does any of the boundaries. So our next thing is that Un is we call this is our Un minus 1, and this is our Un, and this is our Un plus 1. So all of these sets are open on X cross Q, and they contain the set n cross Q. Since Cn is not rational, so n cross Q would be a bunch of points lying here, wherever we have a rational number, and yeah. And if U is the union of Un, then it is open since each of the UNs are open, and it is saturated with respect to P cross I because it contains the entire set C plus cross Q for each little q in big Q. The statement follows from this statement. Since for every n we'll have every Q, basically, for every n in the Z plus. And now what we have to do, we have to prove by contradiction that U prime, which equals P cross I of U, is not open in X star cross Q. Okay, so I think this. So we know that U contains Z plus cross Q for every Q in big Q. This would mean that I will write here on the top because I have some white space here. So we have Z plus cross 0. So just when we prove by contradiction, we start by saying that, okay, U prime maybe is open and X star across Q. So yeah, Z plus cross 0 is contained in U. And this follows that U prime contains an open set of the form W cross I delta. And Y is a neighborhood of, wait, did I put them the other way around? Because this doesn't make sense. Okay. I'm sorry, I just need to recheck my notes. Okay. So W would be a neighborhood of E. And Y delta would consist of all rational numbers Y, where the absolute value of Y is more than delta. And from there we get that P inverse W cross I delta is a subset of U. So if we have our Cn large enough, so it is smaller. If we have our n large enough, so our Cn is more than delta, since P inverse of W is open in X and it contains Z plus, we can then choose epsilon smaller than 1/4, so that n minus epsilon to n plus epsilon is contained in P inverse of W. And from this follows that U contains V, which equals n minus epsilon to n plus epsilon cross I delta. And basically here is our set V. Sorry, this, and we can see that there are loads of points which are only in V, not in U, but V is supposed to be a subset of U. So this would mean that U prime is not open on X star cross Q, And from there, we get that our P cross I is not a quotient map. And this is my last example. We would probably have had some bubble tea to celebrate the end of chapter 2 if we were on campus.
Yeah, that's really great. Thank you.
I want some bubble tea. We don't have bubble tea in Kazakhstan.
I can't even explain to my mom what is bubble tea.
Did she get it?
No. But I tried making her milk tea since we never drink milk tea here, and she actually liked milk tea. So I must consider.
Okay. Then we're meeting on Friday, and we're sending. Yeah, how about we make like a little Google Doc where we just put the names of numbers of problems from each subchapter we did. Yep. And it doesn't have only to be problems. It can be like some theories we didn't prove or we didn't understand or whatever. And then we just publish them so people can look at them beforehand. And then we meet on Friday to discuss them.
Yep.
Also, who is presenting the third chapter? Like, I'm completely confused over the order now.
Third chapter, I think we just followed the order before. 23 is Holly and 24 is you.
24 is me? Okay, I have to remember that. Sure. Okay. Then I'll probably go right now because I have to go cook. I mean, continue cooking, but yeah. See you later, guys.
Okay, see you. But probably
See
we
you.
better assign some kind of host or chair for the problem solving session on Friday, so that we will have someone to make sure that everybody will try to do something. Okay, maybe anyone who want to be the chair.
Wait, I'm not sure. What does that person do?
Well, this person just host this kind of problem-solving session. Okay, who will do next? And how about this problem, this kind of thing?
Can we make it like we put our problems in the Google Doc and people just put their names after the problems they want to do, so they kind of take the responsibility to solve them and show them to the others?
That works. That works.
That would be great. But then, well, I think one just comments on this. So don't try to put too many problems on yourself, okay? And because problems could be easy, could be hard, okay?
Okay. Then see you on Friday, guys.
Okay, see you guys on Friday.
Bye-bye.
Bye, see you
Bye.
Friday.
Bye.